Hello again, chemist. Jolly again. Hey, this is the second part of the kinetics discussion. We are going to continue on with concentration and rate. So I'm going to go back to our notes. All right. So before we talked about the rate of reaction equation, now we want to talk a little bit about the change of reaction rate with time, and we're going to move into then the concentration. So here's just a generic set of data that I got from a book. So here's my concentration, and then I gave you the time. Now, mathematically, at every given moment, I could find the slope. Okay, remember the rise over the run. Which, okay, Jolly, that's very interesting. Why are you telling me that? Because remember, rate is the change in concentration over the change in time. So this would generically be one of the rate equations. Now, if I graph that data, there's a problem because that's not a linear line. What happens in a reaction is here you start with all of your reactants, and it goes really fast at first, but then it tends to slow down. So initially, most reactions tend to go faster and then slow down, which means you're going to get a curved line. So if you want to know anything about any of those times, you're going to have to draw a tangent line. So right here, I drew this wonderful tangent line, and then I found two places that seemed logical to get data from, and I could figure out the slope. All right, that's the old way to do it. Okay, that's the old way to do it. We are now going to do some manipulation to figure out concentrations, the nature of the reactants, like it's called the collision model, whether it's solid, liquid, or gas. We're going to talk about the temperature. We're going to talk about catalysts. We're going to talk about surface areas. And then last, we're going to do these reaction mechanisms. But let's talk about those concentrations first. Okay? All right. Wouldn't you like to know something about the rate and the concentration? And that has a new name. Okay, so I'm going to call this one the rate law. And this is not a jolly term, it's its actual name. A rate law equation, it relates the rate of the reaction to the concentration. Now, the key to this is we are only going to be using the reactants. Because where's the fastest point in any reaction? It's right there at the beginning. And so really I'm not caring about the products being formed. I'm worried about those reactants disappearing at the very beginning. And so this equation is not going to include the products. It's only going to include the reactants. And we're going to set it to the concentration of the reactants. And this is a nice little approximate. Well, do you know what temperature it is? Do you know what pressure it is? Do you know all these details? I'm going to have to take that into account, okay? But also, I need to know how important each of these reactants are, and that's called the coefficient, not coefficient, the exponent, and it's also called the order. Huge, 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 huge. Okay, those exponents, I don't care what variable you use, they are not the coefficients. They are not. They have to be determined experimentally. And I will show you how to do that in just a moment. All right, this approximate sign, well, I'm going to put a constant in here, and we're going to call it the rate constant. This is a small k, and it takes into account all the specific things about that reaction and its temperature. So a generic rate law is the rate is equal to this constant, and then it's the reactants raised to an exponent, an exponent. All right, let's go to that one that we had done before. All right, so N2O5 goes to the 2NO2 and the half oxygen. Well, the rate law is equal to, again, just a constant and only the reactant. And this time I use the variable X. Use whatever variable you would like. That is something I call the generic rate law because I don't know any of the values. How could we find those? Well, we'd have to have some experimental data. Now, if you have two reactants, it would just be the first reactant to X, the second reactant to Y, or again, whatever variable you would like. They are not the coefficients, okay? These exponents are not the coefficients. So what are they? The exponents, okay, yes, they are not the coefficients. They must be determined experimentally. They're generally whole numbers. But they can be negatives or fractions, but not in our class. Okay, so we're always going to use positives and they're going to be whole numbers. And they are used to determine something called the order of the reaction. The order of the reaction describes the effects that it has overall. So I call that the importance. How important are you to the overall reaction? And that is basically its order. Every reactant has its order, and then you add those up to get the overall order. So zero is called zero order, first order, second order, and third order. And so let's go back to our fun little equation here. This is the rate of reaction equation. Why would we use it? If we want to relate all the species together. This is the generic rate law. Notice it has a K and it has an X. Okay, I'm telling you this. This is given now. From experimental data, I found out that the X is equal to 1. So I now put the 1 right there, and there's only one of them, so it's first order N2O5, but also first order overall, because there's only one. That is the way that you come up with the different, exponents. Now, this one was given. They won't always be given. You're going to have to determine them. How am I going to do that, you say? All right. Well, it depends. How many of them are there? So if you only have a single reactant, or do you have multiple reactants, you have to have experimental data. And this calculation, I'm actually going to do in another video, but they go together. So what is the rate law and what are the orders? That's what we just talked about. And in the next little video, I'll actually do the math using experimental data to show you how to determine what those exponents are and also how to determine the x's. All right, until next time, jolly out.